Hi everyone, welcome back. So we aborted the study of number theory from a computational perspective. The motivation was the development of public key cryptography, which needed this rather different set of methods and tools relative to the symmetric crypto we studied earlier. As a motivating example, we gave the Diffie-Hellman key exchange, where two parties can, without knowing any a priori secret information that they jointly share, come into possession of a shared key which the adversary can't figure out from seeing the messages that went between them, which is something quite remarkable. Then towards explaining the elements of that protocol, but also towards seeing how we would implement it, we talked both about number theory mathematically and about it algorithmically. And we reached this point where we have now a whole bunch of algorithms to perform various operations on numbers. Some of them are simple, well-known operations from middle school: integer addition, multiplication, integer division, returning a quotient and remainder. But what we see here is their running times from a theory of algorithms perspective and asymptotic complexity. Remember that these bars around what's here a number return its binary length, meaning the length of the bit representation. In that metric, addition is linear time, multiplication is quadratic, integer division is quadratic, and so on. We often use the mod operation, also quadratic. We had also defined the extended GCD function. We had talked about how that leads to an algorithm that in quadratic time computes the inverses in the group of integers Zn star. Given a point A in that group, it returns the modular inverse. And the modular exponentiation operation, which is a special case of the general group exponentiation operation, are heavily used in encryption. This one has a cubic running time. This one has a time that's linear in number of group operations, which implies this. You can use these algorithms as you need and see fit in solving problems and writing code. Okay, so having algorithms and the ability to compute on numbers isn't the only thing we need to get some cryptography going. At the heart of any cryptographic primitive has to be some problem that is computationally difficult for an adversary to solve. There must be some task that would take it prohibitive computational effort, and our security would rely on that being the case. So whenever we have crypto, we have to seek these hard problems. Effectively, we find them and then we turn them on their head to create crypto. So within the realm of number theory, we're now going to start looking for these kinds of problems. And the problem, the main one in this area, is going to be the discrete log problem. It's going to take us a little bit of math definitions and so forth to get there. But again, perhaps the surprising thing is how little. It's not really that far off. It's elementary algebra from the first couple of weeks of a math class. So remember, we defined groups. So let G be a group and let M be its order. Remember, that's simply the size, the number of points in the group, which you assume is a finite number. And let little g be an element of the group. When we put these braces around G, what it returns is a set. And the set is all powers of G. These are all group elements obtained by raising G to different integer powers. The integers could be both positive or negative. Negative, remember, means that we are dealing with the inverses in the group. Now, defined like that, it may seem that that's an infinite set that it's got, because this exponent raises over the infinite space of all positive and negative integers. But what this fact tells you is that there are actually at most m points in it where m is the group order. That's because a lot of these are just the same. You get a lot of repeats in this sequence. So when we consider these powers, we can in fact restrict attention to exponents that lie in the range 0 through m minus 1. Now, it turns out that extending some of the number theory facts we've seen, we could ask about the size of this set. Although there are m choices for the exponent, that doesn't mean the set has size m. That's the maximum size. Even within this set, there could be repeats. So the size of the set could be smaller than m. In fact, there could be just one point in this set. No matter what, it turns out that the size of this set cannot be an arbitrary number. It has to be something that divides the group order m. So for example, if you have a group of order 12, this set, no matter what g you choose in the group, can never have size 5. Now, that means that for some choices of g, maybe this set has size, the full maximum size m, and sometimes it's smaller. Those g for which it has size m are ones that are special and we like them. We call them generators, or as per the video also a primitive element. So g is a generator if this set has size m, but another way of putting that is that this set equals the entire group. After all, if it's a subset of the group of size m, then it has to equal the entire group. And what that means is that every point in the group is some power of little g. If you look across the group, some points will be generators according to this definition, but some may not. We call a group cyclic if that has some generator, meaning there exists a point in the group such that g is a generator of the group. Not all points in the group need have this property. There may be a generator and plenty of other points that are not generators, and there may be no generator at all, in which case the group is not cyclic. These are, maybe if you haven't seen them before, it's a lot of new terminology, but none of the concepts are particularly deep or heavy, and so if you go through them iteratively, it should sort itself out. Let's play with an example to see how this plays out in a particular group. So the group I look at is the integers mod 11 and relatively prime to 11, z star 11. It consists by definition of all numbers between 0 and 10 that have no common divisor with 11. But since 11 is a prime, that actually leaves us with the numbers from 1 through 10, and so the group has order 10. This is a very familiar number of fingers on our hands, and what we're now going to see is a whole bunch of properties of these numbers that are quite novel, not things we usually think about when we look at the fingers on the hand. The group is z star 11, means operations are done modulo 11. However, note that the size or order of the group is 10. It's one less than the number relative to which operations are done. This is always true when you're looking at a prime in the subscript here. What we're going to do now is take some points in the group, I'll choose 2 and 5, and just generate all their powers. We'll raise them to every possible power. So for the power 0 up to 10. Now, we know that when we get to 10, 2 to the power 10 or anything to the power 10 will just be 1. Why is that? Because we had a fact that any point in a group raised to the power the size of the group will give you back the identity element. The computation is mod 11 because that's the group operation. Okay, let's go ahead. So 2 to the power 0 is 1, 2 to the power 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16, but we are modulo 11, so 16 modulo 11 is 5. Now already it may start getting a little tedious to do 2 to the power 5 mod 11. So we notice that there's a simpler way to do this. Moving from one square to the other is just multiplying by 2. 2 to the power 5 is twice 2 to the power 4. So to move from here to here, I just have to double what's here and take it mod 11. So 2 times 5 is 10. 2 times 10 is 20. 20 mod 11 is 9. 9 times 2, 18, mod 11 is 7. 7 times 2, 14, mod 11 is 3, and so on. Let's also do it with 5. 5 to the power 0 is 1 by definition. 5 to the power 1 is 5. 5 squared is 25. 25 mod 11. 22 is a multiple of 11, so 25 minus 22, and we get 3. Again, at this point, we may be a little lazy about raising things to the raising 5 to various powers. So what's the trick? 5 cubed is 5 times 5 squared. Every time we move up, we're multiplying by 5. So to get here, we multiply 3 by 5, 15. 15 mod 11 is 4. 5 times 4 is 20. 20 mod 11 is 9. 9 times 5 is 45. 45 mod 11 is 1. Now, we could keep doing that, multiplying by 5, but actually, having got a 1 here, we notice that it's even simpler. After all, if the result here only depends on what's in the prior square, we would have to repeat ourselves. We expect this entire sequence to just repeat over here. And indeed, that's what happens. So now that we have these powers, let's form these sets that we saw defined on the prior slide. The set corresponding to 2 is everything in this row. If you look at the things in this row, you notice now that it's everything in the group is there. 1, 2, 3, 4, 5, 6, 7, 8, and where's the 9, 9 and 10. And so I've listed them here, but I've just reordered them to make it apparent that all the integers 1 through 10 are there. For 5, the set is smaller. It has 1, 5, 3, 4, 9. I wrote them in order. And that's it, because then you just repeat. That shows us that these sets can have different sizes. What does it tell us about generators? 2 is a generator. Why? Because this set is the entire group. What is the group? It's whatever's written up here, and you pattern match. Is 5 a generator? No, because this set is not the entire group. In terms of sizes, 2 is a generator because this set has size 10. 5 is not because this set only has size 5. Notice that both 10 and 5 are divisors of 10. We could not, for example, have had this set contain only 4 elements. Whatever you get as a set of this type has to be of an order that divides the size of the group. Is the group Z11 star cyclic? Yes, because it has a generator, namely 2. Now, 5 is not a generator. Does that matter? That's irrelevant to this fact. There is one generator. That's all we need to know. This little exercise will have you do similar things for other groups. So we're looking at now at arithmetic modulo 10 and the group of integers relatively prime to 10. And you're supposed to play with that and determine if the group is cyclic or not. This is the definition of the discrete logarithm problem, now made possible by the definitions we have. We take a group, but we assume it's cyclic as defined earlier. So for example, Z star 11, and we let little g be a generator of the group. So writing this says G is a group generated by little g. Let M be the order. Now, the fact that G is a generator means that if I take any point A in the group, there is some power to which I can raise G to get back A. Furthermore, if I confine the powers to the range 0 through m minus 1, then that choice of exponent is actually unique. And all this follows from our prior definitions, and you should check that you understand why. And due to this uniqueness, we can call I something which is and determine it as a function of A, and that's the discrete logarithm of A to base little g. So this notation with the subscript having the group and the generator says that if you give me a group element A, I return the unique integer I in this range such that this equation is true. This function is the inverse of the exponentiation function. Suppose I consider taking the group element g and raising it to some integer power I in the range Zm. This is some group element. So this function would return its discrete log. But what is the value of that discrete log? Well, if a is g to the power I, then I, by definition, is the discrete log. So the discrete log of g to the power I is I. Similarly, what happens if I raise g to the power the discrete log of some point a? By definition, this returns I such that g to the I is a. So when I raise g to that power, I'll just recover a. So these two operations thus reverse each other. Let's look at an example of discrete log computations. So we'll go back to our example of integers mod 11. The set is the numbers 1 through 10. And now we know it's a cyclic group. It has order 10, and we know that 2 is a generator. So the discrete log base 2 of anything in the group is now well defined. But let's try to figure out what it is. By definition, it returns the unique I such that 2 to the power I is A in the group. Since the group is mod 11, that means 2 to the power mod 11 is A. The range of I is in Z10 because it ranges from 0 up to 1 less than the order of the group. The order of the group being 10, it stops at 9. So let's first just copy down our table of raising 2 to various powers. From the prior slides, I've listed here various exponents, and I've stopped at 9 because if I go to 10, I just get back 1. 10 is equivalent to 0 that way. And here's 2 raised to these powers. I want another table now where for every group element, I want its discrete log. The group elements are from this set, so they go from 1 through 10. And I want to know the integers which are their discrete logs. What I'm asking here is, how do I get 1 by raising 2 to some power? That's easy. 2 to the power 0 is 1. How do I get a 2? Well, 2 to the power 1 is 2. How do I get a 3? That's a little more tricky. To what power do I need to raise 2 mod 11 to get back 3? But then we notice that this table tells us that. In what way does it do that? It says that 2 to the power 8 is 3. So that means that the discrete log of 3 is 8. More generally, it simply says that this table is this table backwards. So I can fill in the entries of this table by just taking the ones here and reading backwards. 3 corresponds to 8 as we saw. For 4, I look for 4 in this bottom list, find it here, so the discrete log is 2. For 5, find it here, its discrete log is 4, and so on. Here's a little exercise about that. So we'll have a group, again, Z star 10, and you're supposed to find some generators, discrete logs, and stuff like that. It's not enough to have defined these concepts. We will need to write software and implement algorithms that work inside such groups. So we need to have examples of them. And this is a few mathematical facts that gives us that. We had seen that Z star 11 is cyclic. The fact 1 says that that's not a coincidence. Anytime you have a prime and you look at integers modulo that prime, then you have a cyclic group. The second fact says, take any group G and figure out its order. So remember, the order is this size and it'll be some integer. If that integer is itself a prime number, then your group will be cyclic, no matter what the group is. So those are both ways to find cyclic groups, and we'll kind of see both arising. A possible point of confusion is that they're kind of the same fact. Why are they not? ZP star, where even though P is a prime, has order what? Not P, but P minus 1. The number of points in ZP star is P minus 1. P minus 1 is not a prime. In fact, for any odd value of P, it's never a prime because it's even. So even though this fact is true, it's not a corollary of this fact. We identified this discrete log problem because it turns out that, to the best of our understanding, it's hard. Adversaries are going to have a hard time computing discrete logs in appropriately chosen groups of appropriate size and type. And towards that, we're going to start thinking about the problem of computing discrete logs. How would we do it? So the problem would be that we have fixed a group, we've fixed a generator of the group. That means the discrete log is well defined. We know its order, and of course we know the group and generator. Now I give you as input some big X in the group, and I ask you, please compute its discrete log. What is it that you want to output? Some little x, such that raising g to the power little x in the group returns big X. This little x would have a value in the range 0 through m minus 1. Well, it seems like there's a pretty easy way to find little x. Why is that? We know that in the range 0 through m minus 1 is where little x lies. In fact, in that range, there will be a unique little x such that this equation is true. So I can just try them all. For every possible value of little x, I raise g to the power little x, and I test if I get back big X. And if so, little x can be returned as the discrete log. This operation is very fast. We know we've studied modular exponentiation. It's time cubic in the lengths of the numbers. So the running time of this algorithm is up to small factors the size of or order of the group. It's m steps. So let's ask if this is a good algorithm. And as we've seen a little bit before, it depends what you mean by good. If you mean it's correct and gives you back the right answer, for sure it does. It will find the discrete log always. The difficulty is that it's ridiculously slow. Effectively, it runs in exponential time because we want to measure time as a function of the lengths of the numbers involved, and it's taking time proportional to the actual magnitude of the number, namely m. And as soon as the groups get relatively big, which is what they're going to be in cryptography, for example, the prime P might be a few hundred bits long, then the size of the group, which is P, let's say P was 128 bits long, the size of the group is about 2 to the power 128. And so the algorithm is completely out of reach. So this is where, if you were an algorithmist, you might get disappointed, and because we like to have fast algorithms, but cryptographers get excited because it means that if this holds up and if this problem really is hard, then potentially we have here something which we can use as a basis of cryptography by somehow making sure that adversaries are forced to solve the discrete log problem. If we want to do that, however, and actually exploit this for security, we need to be a little more careful than just saying, well, we looked at this obvious way to do it and that failed, so let's assume nobody can take discrete logs quickly. The fact is that we spent very little time on this, and maybe there are better algorithms which are not obvious. This happens, for example, for modular exponentiation. Also, our first algorithm had been exponential time, but then a little thought showed a cleverer, very fast polynomial time algorithm. Is the same thing true for discrete logs? Actually, we don't know. We don't have any proof that there isn't a fast algorithm, but people have tried quite a bit, and what this slide represents is the best we know. It turns out that the algorithm we saw is not at all the best possible. If you want to compute integers in ZP star, there is a much faster algorithm and more non-trivial one. What is its running time? E here is the base of the natural log, about 2.7. The running time of your algorithm says take the natural log of P and take its cube root. then take the natural log twice and take that to the power 2/3 and raise e to that power with some constant. This is what we call a sub-exponential time algorithm. It's not exponential would be if these powers 1/3 and 2/3 were missing, but so this is faster than exponential, but still the running time grows very swiftly with p, and it gets slow quite quickly as p gets larger. Now it turns out that depending on what type of group you have, the time for computing discrete logarithms changes. There's something called an elliptic curve group, and here we are talking about ones whose order is a prime number p. And it turns out in these groups, the best known algorithm for discrete logs takes time square root of p. To compare to the above, write that as e to the power half of log p. And now you see that because of the cube roots here, this is a much bigger number than this. And so this says that the algorithm here is slower. From the crypto point of view, that's better. We can get somehow more security here than here, at least for a given size of group. Now there are various caveats associated with these running times. One of them is that in the first case, this is only true for primes which have some appropriate structure. The actual running time doesn't have a p here, but q, where q is the largest prime that divides the group order p minus 1. So to make this true, you better make sure that p minus 1 has a large prime factor, and that's what we do when we pick them. Remember that all of this represents only the best we know. It could be that there exist better discrete log algorithms, but it's just the case that we haven't found them yet. So if you want to see how these things work out, you can go on the internet and find discrete log calculators. So you could give it some base, maybe 2, some modulus like 11, and then some number, and see if it computes a discrete log. And it says the result is 6. No, that's digits per group, okay? It says the result is 4. And what they mean by that is 2 to the power 4 should be 5 mod 11. And is that true? Let's see. 2 to the power 4 is 2, 4, 8, 16. 16 mod 11 is 5. So it did well there. But how far can this thing go? And what did I get there? Let's see. This tells you something about the algorithm. It says it uses Polig-Hellman. That's one of the discrete log algorithms. And so the execution time is proportional to the square root of the largest prime factor of the modulus minus 1. So this is actually slower than the algorithm whose running time I showed you on the slide, right? It actually has this type of running time, even though it's working in these groups, and they do exist fast algorithms. And the person said they'll add them later, actually. But then it says that this applet works in a reasonable number of times if this factor is less than 10 to the 17. Okay, well that's not a very large number. So in fact, how much is 10 to the 17? Maybe a few tens of bits. That's about it. And we are thinking about numbers that are hundreds to thousands of bits. So you can see how these things are going to be too slow. Now, these asymptotic or theoretical runtimes are not the whole story. What is needed in practice is also, how do I pick a size for the prime or for the group if I have an intended target of security, in the sense that if I want the adversary running time to compute discrete logs to be, say, 2 to the power 80, how big a prime do I need for that? So people evaluate this experimentally. They have primes of different sizes and they run these algorithms, optimize as much as possible using as good hardware and software as they have parallelizing it as much as possible to see what they can do in terms of finding discrete logs. These are often take the form of challenges. Various entities publish challenges and pay out money if you find the discrete logs corresponding to the challenge. So you see here that when the bit length of P was 430, by 2005, they were experimentally able to find discrete logs. And then that went up by 2007, up to 530 bits, and almost 600 by 2014. Now for elliptic curves, the algorithm, as per our prior slide, is slower. That means that P, which there is the size of the group, can be quite a bit smaller and nonetheless it will be hard to find discrete logs. It appears the best people have been able to do there is find discrete logs when the group has size about 2 to the power 113. So more detail about that can be found on the internet. So this is just a Wikipedia article on discrete log records. And they tell you about integers mod P, and you can see that I'm pretty out of date. For example, just at the end of last year, there was a computation that actually found the discrete log modulo 795-bit prime. That's pretty remarkable and quite a bit beyond what one might imagine. A few years before that, 2016, they had done 768-bit primes. Nadia Henninger is a professor in our department, by the way. See, as the blurb says, UC San Diego, we're very proud to have her here. This also shows you discrete log computations in other groups and fields. And here you see the elliptic curve results, and let's see where they've gotten up to. They talk about the different challenges, and here they talk about 108. I was under the impression that it had gone to 113. Oh yeah, the discrete log of 113-bit Koblitz curve. It's done over here. So there's lots of nuances in this stuff. Now, what is the impact of the fact that different choices of groups, integers mod or prime versus elliptic curves, have different discrete log running times? The impact is cost of algorithms. The punchline here is that if you work in elliptic curve groups, you can get the same security while having systems that encrypt quite a bit faster. And what this says is that if you're interested in 80 bits of security, meaning the adversary should have to spend 2 to the 80 effort to break your system, and it's discrete log based, if you work with integers mod or prime as your group, you would have algorithms and encryption which is 260 times slower than if you worked in an elliptic curve group. So for performance reasons, that makes elliptic curves preferable. How do you get these estimates? You ask yourself, how big does the prime P have to be for a group ZP star before the effort to compute discrete logs hits 2 to the 80? So since this is the running time of the best algorithm, you're effectively saying, how big does P have to be before this hits 2 to the 80? And the answer is something like 2 to the 1024. And on the other hand, since the best algorithm elliptic curves can reach that kind of effort already when the group has size only 2 to the 160, then you have this facts about the group size. So I can either have elliptic curve group of this size or a group of integers mod or prime of this size, and security-wise they're the same. But what about costs? Well, exponentiation is the main cost for encryption, and we saw that this as a cubic time algorithm. This means that the cost is roughly cubic in this exponent. So if you take the ratio of these two exponents and cube that, you'll get 260. And that tells us that the exponential will be that much faster over here. Now, there's a lot more to know and understand about the practice of things like discrete logs when you're setting up systems. Here was an interesting paper that appeared a little while back. It corresponds to what's called the logjam attack. And what this says is that if you consider the algorithms for computing discrete logs mod of prime, it's true that they have the running time we said, but they're very structured in the following sense, that the bulk of the computation only depends on the prime p. The result is that if you want to compute modulo a single prime thousands and thousands of discrete logs, it's not going to take you too much more time than computing a single discrete logs, because you would do a massive pre-computation on the prime and then very fast individual discrete log computations. That's what this thing showed. So they evaluated all this experimentally, and they were actually able to break some standardized systems and also sound quite a bit of a warning and make some interesting conjectures about whether various national security agencies are able to do things like this and so forth. So quite interesting reading.